This is going to be the last official section that we do in Chapter 11, but as I said, I really think it's fun to do density, so we'll be doing that as well. But this is on ratios with 3D figures. So I want you guys to think back to what we did last chapter. The first problem to start thinking says the ratio of the corresponding sides of two similar triangles is 2 to 3. The area of the smaller triangle is 100. What is the area of the bigger? So if they give me the ratio of 2 to 3, what do I have to do to that to be able to solve for an area? Does anybody remember? You got to square it. So you cannot use it as is. You square it, and that goes over and gives you 4 to 9. All right? Then you can go over and say, all right, well, it was 100 for the smaller one. What is the bigger? I had a lot of people who set this up wrong. So they put small over big on the test, and then they put big over small on the other fraction. So just be careful with that. That gives us 900 equals 4x. And when we divide by 4 and divide by 4, we get, some with the calculator, have to have a calculator for today's lesson. 225? Okay, 225 inches squared. So we've already done that. I know that I've hinted on what we can do with volume, but we're going to be looking at that right now. So we're talking about similar solids today. What that is are going to be 3D figures that have the same shape, but not always the same size. And the main thing here is that all of the sides are going to be proportional. So if you have two figures and you're trying to figure out if they're similar, you would look at all corresponding sides. For example, 3 corresponds to 6. So that would be the ratio if it is similar. Let's see if all of the other sides are proportional. So 3 corresponds to 6. The bottom one is 3 and this one's 6, so it's 3 to 6. And then we have 2 corresponds to 4. Do all of those fractions reduce to the same thing? Yes. Then they are similar figures. And you would be able to use the rules we're about to develop for ratios of similar figures. Now let's look at this next one. 2 corresponds to 3. Cool. 3 corresponds to 6. And lastly, 2 corresponds to 3. Are all of those equal when you reduce them? No. So that would be no, they are not similar, and the rules we're about to come up with would not work for these. Anybody have any questions? So what we're going to do now is we are going to try to figure out, if we know the ratio of the sides, what happens to the other ratios. So I'll help you with the ratio of sides really quickly. This is 5 and this is 10. So the ratio of sides for this one would be 5 to 10, which reduces to 1 to 2. Also meaning just the sides became twice as big. Now on the other one, it's going to be 5 and this one is 25. So the ratio is 1 to 20, or what is it? 5 to 25, which reduces to 1 to 5. Right? 5 to 25 reduces to 1 to 5. Okay, to speed up this process so we can get to the practice problems, I'm going to assign some groups to do the surface area and volume of this, some groups to do the surface area volume and for this one, and surface area and volume for this one will be other groups. And then what we're going to do is we're going to look at all of the ratios. Okay, so what did we get for the surface area of the original? 62. Everybody agrees? Great. What'd you get for the volume? 30. Okay, cool. Now let's go to the next one. What'd you get for a surface area? 248. What'd you get for the volume? 240. What'd you get for the surface area of the last one? That is correct. And what did you guys get for the volume of that one? 375. Okay, so what we are going to do now, we already have the ratio of the sides reduced. Let's do it for surface area. I need you guys to put 62 divided by 248 in your calculator in Math Bracket. 62 over 248 in Math Bracket. What do you get? 1 to 4. Great. Now do 30 to 240. Let's find out what the ratio of volumes is for that. 30 over 240, math fract is 1 to 8. Math frac means press the math button, press frac, and it reduces your fractions for you. It's really nice. Now what I want you to do is do 62 to 1550 in math bracket and see what you get. 1 to 25. Now do the 30 and compare it to the new volume in math bracket and see what you get. What is 30 over 3750 math fract? 1 to 125. Fantastic. What we are looking is to try to find out what is the pattern here. If you knew the sides, what do you do to the ratio of sides to get the ratio of surface areas? Look at both of these. What does it appear that you did to the sides to get surface areas? Square root? Squared it. Fantastic. So it is going to be squaring. We already learned that in our last chapter. Now take a look here. What can we do to 1 to 2 to make it a 1 to 8, which is the same thing you do to 1 to 5 to make it 1 to 125? You cube it. Fantastic. Okay, so let's go ahead and put that down below. This is the most important stuff. If you know the ratio of the sides is a to b, then areas is a squared to b squared. When they give you sides and you're solving for surface area, you would square it. If they give you sides and you want to find a volume, you are going to cube it. Here is basically the visual interpretation of what we do. This is ratio of sides, that's the ratio of areas, and that's the ratio of volumes. To go from sides to areas, you square it. To go from sides to volumes, you cube it. How do you undo squaring to get from areas to back to sides? Square root. And one other thing, how do you go from volumes to sides? What do you do to uncube something? Cubed root. We cubed root it, also known as raising it to the 1/3 power. That is like if I was making a one-pager, that's what I'd put in it. Also a visual interpretation of the whole, like, wait a second, you said if it's 2 times as big for sides, the volume is 8 times as big? That makes no sense. Well, let me show you visually. Here is a cube. I'm going to double all of the sides, doubling all the sides. This is the resulting figure right here. When I doubled the sides, how much bigger did the volume become? 1, 2, 3, 4, 5, 6, 7, 8. That made sense. When I doubled sides, the volume actually became 8 times as big. Does that make sense? Okay. Let's go ahead and do some practice problems. So what they're going to do is they're going to give you a ratio with both of the numbers. And you're going to have to change that ratio for whatever you are solving for. So the first one says the smaller pyramid has a height of 3 and the bigger one has a height of 5. The surface area of one is 100. What's the surface area of the other one? Did they give me the ratio of sides, areas, or volumes? What are heights like? Are heights like sides, surface areas, or volumes? Sides, I agree. So they gave us the ratio 3 to 5, but we can't use that. We are solving for an area. What do we do to this one to go from sides to areas? Square it. So we're going to square it, and that gives us 9 to 25. Now we finally have something we can work with. I saw a lot of kids on the test accidentally, they would put small over big for this ratio, and then they say the smaller one has an area of 100. They accidentally would put that on the bottom for some reason. So this is going to be 100 up here, and there's your x. Once again, the ratio they give you most times will not be what you can use. You have to adapt it. That gives us 9x equals 2500, and someone with a calculator is going to do the dividing by 9 and getting x equals 277.8 inches squared. Does anybody have any questions about why I adapted the 3 over 5? No? Okay, let's look at the next one. Looking at this one, They say the surface area of the smaller cone is 49, the surface area of the bigger is 121. If the volume of the smaller is 200, what's the volume of the bigger? They gave us, Carson, what they give us both of the numbers for? The ratio of what's? Did they give us the ratio of sides, surface areas, or volumes, where we got both of the numbers? Surface areas. So they gave us 49 over 121. That's surface areas. But we are solving for a what? Volume. So looking back at our little track here, how the heck do we go from surface areas to volumes? Is there an area that, or an arrow that goes straight from surface areas to volumes? No, we need to go back to sides. And once we go back to sides, then we can go to volumes. So how do we go from surface area to sides? Square root. That gives us 7 to 11. That's the ratio of sides now. And what do we have to do to those to be able to have the ratio of the volumes? Cube it. So we're going to cube this one, and we're going to cube that one. 7 cubed is 343. 11 cubed is 1331. That does not mean that one volume has to be 343 and one of them has to be 1331, which means that's the ratio. So now when they say, see, like the smaller one is definitely not 343, they tell us that it's 200. So I'm going to put a 200 there, and then I put an X here. And now we just do our basic algebra 1 stuff. 200 times 1331 is 266. 200 equals 343x. And when we divide by 343, you said you got what? 776.09, so 0.1. Divided by 343, I got 776.09, so 0.1. Try again. I don't know, you put it in your calculator wrong or something. Does anybody have any questions on that one? The next one's a little bit funkier. Are you sure nobody has questions on why I had to go back to sides or anything like that? It's kind of like how we never go on a 30, 60, 90 across the 30. There's actually a way to do it. It's just confusing. Okay, on this one, Henry, what is the ratio that they gave us both the numbers for? The volume of the smaller is 230. The volume of the bigger is 500. If the height of the smaller is 10, then what's the height of the bigger? What are they giving us both the numbers for? Volumes, sides, or surface areas? Well, let's take a look. They said the volume of this one is that number, and the volume of that is this number. Do you see how they gave us both of the volumes? Henry? Yeah. Okay, so they gave us already the ratios 230 to 500. Always math frac things. So if you math frac that, I already have done it. It gives you 23 to 50. The reason we math frac it is, like in this case, what are we going to have to do to this ratio to get back to sides? How do we go from volumes to sides? We do cube root it. Well, I already know that 230 is not cube rootable and 500 is not nicely cube rootable. So I reduce it and hopefully it becomes cube rootable. In this case, no, it does not. So all we're going to do is we're going to leave it as the cube root of 23 and the cube root of 50, because we are going from volumes to sides. And now we can use that ratio. They say the smaller is 10, the bigger is x. And don't freak out by like cube root of 23. Well, what do I do with that? Just do what you would do if it was a normal easy number. Cross multiply. When we cross multiply this way, you get cubed root of 23 times x equals, the other way is 10 times the cubed root of 50. And everybody should practice putting this in your calculator. So the way we're going to do this is just do the cube root of 50, enter, then multiply by 10, enter, and then divide by cube root of 23, just like you would do if those were normal numbers. As everybody is putting it in your calculator, you should have 50 to the 1/3 power. You guys should get 3.6840, blah, 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 blah. If you got that, great. If you got 12.9, my guess, you said you already did you did 50 to the 1/3 power? Then you did not use parentheses in your calculator. Try it again. Do 50 to the 1/3 power again. Because a lot of times, let's see, 50 divided by 3, I don't know why you're getting, if you do 50 to the 1/3 power, you should get 3 point, yeah, we're going to do that. I'm not there yet. To the 1 divided by 3. That gives me, I'm just going to go through the whole thing really quickly. 3.684, you're going to multiply by 10. That gives you 36.84, blah, blah, blah. And now you're going to divide by that cubed root of 23. 23 to the 1/3 power. And your final answer is 12.95. Is that what you were saying? Your final answer? Yeah, I was telling you what it was midway through the problem. So about 12.95 inches. Yeah, I'm just starting to round it like random places. I should probably stick with something. Does anybody have any questions? No, because we're solving for a height. Does anybody have any questions? Let's do this one last problem, and then I'd like you guys to do some practice. It says, you decide you're going to blow up a spherical balloon. You guys one day will be a parent, and you've got these little runt kids, and you're going to go over and blow up a balloon for them, and they're not going to be happy with it. They're going to be like, no, I want it bigger. And they ask you to go over and make it twice the radius. So they want you to make it twice as big. The question becomes, what happens to the surface area? And more importantly, what happens to the volume? How much extra breath are you going to have to put into this thing? So 2x for sides, what does that make it for surface areas? What do we have to do to the 2 number to figure out what happens to surface areas? Square it. So how much bigger will the surface area be? What's 2 squared? 4 times as big. And what happens to the amount of air you're going to have to put in that thing? When you double the radius, does the volume just double? No. What do you have to do to the 2 to find out what happens to volume? Cube it. So when your little kid asks you to go over and make the radius twice as big, or he wants his balloon twice as big, you're going to put 8 times as much area. Let's say he asked for it to be 3 times as big. That means the surface area, which you don't care about much, will be 9 times as big, but you're going to have to put in 3 cubed, 27 times as much air just to make that thing 3 times as big. That's pretty crazy. Does anybody have any questions? What I'd like you guys to do right now, we have about 7 minutes left. Go ahead and try to crank through the problems below. People at home, pause the video and try to crank through these problems, and we'll go over the answers in just 1 second. All right, on this first one, they give you the ratio 27 to 125. That's volumes, and you want to solve for a side. So you're going to cube root the ratio. That gets you to 3 to 5, and then you set up your ratio, and when you solve, you get 4.8. The next one, they gave you the ratio of sides, which is 5 to 7, but you're solving for a surface area, so you need to square it. The ratio that's actually going to work for you is 25 to 49, and when you solve, you get 294. The next one, they give you the ratio of surface areas, and you're solving for a volume. If you're going from surface area to volume, you're first going to square root to get to sides, and then you're going to cube it to get to volumes. Now we have the ratio of volumes, and you can set up your proportion and solve. And when you do this, you get 109.85. And lastly, when you quadruple sides, you got to take that 4 and square it. That gives you 16 times as big for area. And volume is going to be 4 cubed, which is 64 times as big for volume. Does anybody have any questions about how to jump around? This is the most important part right here. This tells you how to jump from ratio to ratio. All right, people at home, thanks for watching.